Hello everyone, I am Mohammad Adil and I am a student of Engineering Physics BTech third year at IIT Roorkee. Today I am here to present one of the experiment in my Applied Instrumentation course, and the experiment is Hall effect. So the aim of this experiment is to find the Hall coefficient and then further use it to calculate mobility and conductivity. So the apparatus that I will be using in this experiment are, as you can see, so apparatus is digital Gauss meter. It will be used to calculate it will be used to show the magnetic field in the electromagnet, and this is the constant current power supply which will be passed to the this electromagnet, and this is the Gauss probe. This Gauss probe will be used to find the magnetic field, which will be shown here, and this is the digital Hall effect set. Here we have got the current and voltmeter reading. This current and voltmeter reading will be in the Hall probe. The Hall probe has the crystal of germanium. So okay, now I have set the current in the electromagnet to be 2 ampere, and I have used the Gauss probe to find the magnetic field corresponding to it. And as you can see, can you zoom here? So as you can see, it is 233 Gauss. So I have taken a reading of it. So for current is equals to 2 ampere, I have got the magnetic field as 232 Gauss. Now I will use it in the further calculations. Now what we have to do next is to find the voltage, that will be Hall voltage in this germanium crystal corresponding to the current that will be passing in it. Now for that we are going to take two kinds of reading. First of all, we'll keep the current to be positive, and for that we'll find the corresponding Hall voltage, and then we'll take the current to be negative, and then again we'll find the corresponding Hall voltage. Okay, so now I have set the current as 1 milliampere in the germanium crystal. Alright, and now corresponding to the 1 milliampere current, what I can see is that there is 0.3 millivoltage of Hall voltage in it. But at right now I have not kept it in any magnetic field. So this is zero field potential. Now this potential has to be subtracted in the values that we are going to get in the further readings. So this has to be subtracted from them. Now I am going to place this Hall probe in the electromagnet. So I will place this in the electromagnet. Now corresponding to 1 milliampere current in the germanium crystal, I am getting 1.9 millivolt Hall voltage. Now from this 1.9 millivolt Hall voltage, we have to subtract that initial error, that zero field potential, 0.3. So the value that we will get finally will be 1.6. Now correspondingly we will change the ampere reading to 2 milliampere, and the reading we will get is 4.6, and from here also we will subtract 0.3. So finally we will get 4.2 and 4 plus minus 0.1. So that's how we will proceed and keep taking readings in the steps of 1 milliampere. And finally we will plot the graph of this value, and finally we'll calculate the Hall coefficient, and from further calculations we'll find conductivity and mobility, which I will show in my lab workbook. Okay, thank you. These are the specifications of the germanium crystal, and these are the readings that we got from the experiment. Now corresponding to these readings, we can plot the graph between the Hall voltage and the current applied to the germanium crystal. These both are in millivolt and milliampere. So as we can see that our plot is a straight line. So this straight line graph, now we can use its slope to find the Hall coefficient. So as we can see, we are using its slope to find the Hall coefficient. After finding the Hall coefficient, we are going to use it to calculate mobility and carrier density. So as you can see, the carrier density comes out to be 5.95 into 10 power 23 per meter cube. Also, as you can see that our RH or Hall coefficient is greater than 0, which helps us to conclude that our majority charge carriers are holes, and this implies that our semiconductor is a p-type semiconductor. So these are the calculations related to the experiment, and I hope this experiment was able to add something to your experience and knowledge, and thank you.